Rate law experiment calculations. Consider this rate experiment. 2N2O5 produces 2NO2 plus O2. The general rate law equation for this reaction would be rate equals K N2O5, which is in brackets for the concentration, to the order of M. To determine the value of M, a chemist performs 3 experiments. A different initial concentration of dinitrogen pentoxide is used for the experiment. The subscript 0 represents T equal to 0. Here are the results. The value of M can be calculated or determined using at least 2 different methods. By inspection, you can see when the concentration of N2O5 is doubled, as shown in experiments 1 and 2, the rate also doubles. When the concentration of N2O5 is tripled, experiments 1 and 3, the rate also triples. So this relationship indicates a first order relationship. So we would write that as K times the concentration of N2O5 to the order 1. Number 2, a second method. Compare the rate law equations for each experiment using ratios. This method is useful when the relationship between concentration and rate is not immediately obvious from the data. So the rate of 1 is K times 0.010 order M equal 4.8 times 10 to the negative 6 mole divided by liter seconds. Rate 2 is K is equal to 0.020 order M equals 9.6 times 10 to the negative 6 mole divided by liter seconds. Create a ratio to compare the two rates. So we have rate 1, we have rate 2, we have the values on the top to match the values on the bottom. Since K is a constant for reactions that occur at a constant temperature, you can cancel out K. Then if you solve, you will get 0.5 to the order M equals 0.5. So by inspection, M is equal to 1. Determining the rate constant. Once you know the rate law equation for a reaction, you can calculate the rate constant using the results from any of the experiments. The rate law equation for the previous rate experiments is written as rate equals K times the concentration of N2O5 to the order 1. You can use data from any of the 3 experiments to calculate K. Substituting data from experiment 1, you can solve for K. So we know that 4.8 times 10 to the negative 6 mole divided by liter seconds equals K times 0.010 mole per liter. So this is going to work out to be K, a value of 4.8 times 10 to the negative 6 mole per liter seconds divided by 0.010 mole per liter, which works out to be 4.8 times 10 to the negative 6 s to the negative 1. So determining the rate constant conclusion, therefore, for the temperature at which the experiments were carried out, 4.8 times 10 to the negative 4 s to the negative 1 is the rate constant. Using data from experiment 2 would give the same value of K. Concept check. Notice that the units of the rate constant are determined by your calculation. For a first order reaction, the units are always s to the exponent negative 1. Show why this is the case. What are the units for a second order reaction? Something to think about. So let's look at a problem. Chlorine dioxide, ClO2, reacts with hydroxide ions to produce a mixture of chlorate and chlorite ions. Given the equation, 2ClO2 aqueous plus 2OH minus aqueous produces ClO3 negative aqueous plus ClO2 negative aqueous plus H2O liquid. The rate data in the table below were determined at a constant temperature. Find the rate law equation and the value of K. In analyzing this problem, what is required? Well, we will need to find the value of M, N, and K in the general rate law equation for the reaction, written as rate equals K, ClO2 to the order M, times the concentration of OH to the order N. Next, what is given? You know the initial concentrations of the reactants and the initial rates for 3 experiments. So now let's plan our strategy. Step 1. Find 2 experiments in which the concentration of ClO2 remains constant and the concentration of OA negative changes. Compare the rates and concentrations to solve for N. Then find 2 experiments in which the concentration of OH negative remains constant and the concentration of ClO2 changes. Compare rates and concentrations to find M. Step 2. Use the data and your calculated values for M and N to solve for K. Using the given equation, K times the concentration of ClO2 to the order of M times the concentration of OH minus to the order N is equal to rate. Now, let's act on our strategy. Step number 1. Begin with experiments 1 and 2, where the concentration of ClO2 is constant, to determine the order of the reaction with respect to OH minus. Set up a ratio for the 2 rates as shown. Notice that you can cancel out the concentration of ClO2 because you chose experiments in which the concentration of ClO2 did not change. So we can then compare rate 2 to rate 1. Because K is constant, we can cancel it out, and we're left with 2N equals 2, N equals to 1. Therefore, the reaction is first order with respect to OH minus. Now, following the same logic, set up a ratio for experiments 1 and 3 in which the concentration of OH is constant and the concentration of ClO2 changes. You will see that you can cancel out the concentration of the OH minus terms right away. And from that, we will get that 3m is equal to 8.92, which is 9. So m is equal to 2. So the reaction is second order with respect to ClO2. Therefore, the rate law equation is written as the rate equals K times the concentration of ClO2 to the order 2 times the concentration of OH minus. This makes the reaction second order for ClO2, first order for OH minus, and then it is a third order reaction rate overall. Step number 2. To find the value of the rate constant, substitute data from any of the 3 experiments into the rate law equation. Using the data from experiment 1 gives the following equation. 1.3 times 10 to the negative 3 mole per liter second equals K 0.015 mole per liter to the order 2 times 0.025 mole per liter. Substitute into the equation and solve for K. We will then arrive at K being 231 liters squared times mole squared per second, or times second. Therefore, the rate constant at the temperature of the experiment is 231 liters squared divided by mole squared times second. The rate law equation then is 231 L squared divided by mole squared times F times the concentration of ClO2 order 2 and OH. The last thing we'll do is check our solution. To check your values of M and N, solve by inspection. When the concentration of ClO2 is constant and OH minus doubles the concentration, the rate also doubles and the reaction is first order in OH minus. When the concentration of OH minus is constant and the concentration of ClO2 triples, the rate increases by a factor of 9. Recall that 3 squared is 9, indicating a second order relationship. To check your value of K, substitute data from experiment 2 or 3. You should get the same answer. Also, check the units and the number of significant digits for K. Now, it's your turn.